Bismillahirrahmanirrahim. Assalamu alaikum, dear students. I'm Arif and I welcome you all to lecture number 10 on the subject of computer organization and assembly language programming. The title of today's session is HDL for Sequential Circuits. Well, today's session will start with the class quiz. Then we will see as to why do we need sequential circuits and the concept of time or clock in our computer systems. We will then have a brief comparison between the combinational and the sequential circuits, and we will also discuss the main building blocks of sequential circuits called flip-flops. The four main types of flip-flops are S, D, JK, and T. But I will spend more time on D flip-flop as we will be using the D flip-flop only for designing the sequential circuits in this part of the course. So let's move ahead. Excuse me. So this is the class quiz. Well, dear students, in the last session we designed the hack ALU, this one, which input two 16-bit numbers and can perform 18 different operations on these two input values based on these six control inputs: ZX, NX, ZY, NY, F, and NO, and generate a 16-bit output and set or reset two flags, ZR and NG, the zero flag and the negative flag. We also practiced how this ALU do the presetting on the X input, the presetting on the Y input, and perform the operation F, and then do the post setting based on the NO bit. I hope you will be able to solve these two problems. So stop this video, solve the quiz, and later join me. And meanwhile, I am moving ahead. Well, up till now in this course, we have discussed in detail about the combinational circuits, their design methodology, and writing HDL for different combinational chips. Let us move ahead today and first try to understand as to why do we need sequential circuits. Well, dear students, so far we have designed and implemented our own ALU using different combinational chips, whose output at any time depend on the current input. The combinational chips we have designed so far, of course, cannot maintain the state. Since computers must be able to not only compute values, but also store and recall values, they must be equipped with memory elements that can preserve data over time. And these memory elements are built from the sequential chips. Dear students, the act of remembering something is inherently time dependent. Thus, in order to build chips that remember previously stored information, we must first develop some standard means for representing the progression of time. In most computers, the passage of time is represented by a master clock that delivers a continuous train of alternating signals using the hardware called an oscillator normally, which alternates between two phases 0 and 1. You can see this is the physical time, which is continuous entity, and this is the clock, which can vary between two values 0 and 1, and this is one time unit, and the elapsed time between the beginning of this tick and the end of the subsequent talk is called a clock cycle. Tick tock, this is one clock cycle. Tick tock, this is second clock cycle. Tick tock, this is third clock cycle, and so on. Well, the current clock phase, tick or tock, whatever, is represented by a binary signal, 0 or 1. And using the hardware circuitry, this signal is simultaneously broadcasted to every sequential chip throughout the computer platform. But so far we have ignored the issue of time, and the chip's inputs were just sitting there fixed and unchanging. and the chip's output was a pure function of the current inputs computed instantaneously. It did not depend on anything that happened previously. So this is the example of XOR gate, that is the time independent combinational circuit having two inputs A and B and a single bit output out. This output depends whatever is there on these two input pins. So there is no concept of actual time. But we need the concept of time. Our hardware must support the state. For example, I want to store a value 17 in a variable suppose x, and I want that I should be able to access it anytime in the future. Similarly, I may like to design a loop in which I am accessing a variable sum in every iteration of the loop. So the hardware must handle the physical time delays associated with calculating and moving data from one chip to the other. Let us try to understand the concept of time. Well, as I have already said, that physical time is a continuous entity. This is the clock delivering a continuous train of alternating signals, a tick, tock, tick, tock. And this is the discrete time, that is 1, 2, 3, 4, 5, and so on. A state change in a circuit occurs only when advancing from one time unit to another. Let us consider a simple NOT gate having an input named in and an output named out. At this time unit 1, the input of this NOT gate is high or 1. So the output shown over here is 0. Similarly, at time unit 2, the in input of this NOT gate is low or 0. So the output shown over here at time 2 is 1. And this process goes on. Well, dear students, this is the ideal or desired behavior of the in and the out signals. And this is how we want the hardware to handle the time dependent behavior. But the actual behavior of the in and out signals are a bit different due to physical time delays, and this is shown over here. You can observe that the actual output of the NOT gate at time 1, the output of the NOT gate is generated after a short delay, shown in gray over here. This delay is due to the propagation of the signals as well as due to the computation delays involved in the gate chip. Well, dear students, this concept is critical, and the duration of the clock cycle from this point to this point is designed by the hardware designer to neutralize these propagation and computation delay. So the length of this clock cycle must be kept slightly longer than these time delays. Otherwise, these computation and propagation delays will create problem. To sum up, let me say that for this combinational chip NOT, it appears from this signal diagram that the gate reacts immediately to the input. But actually this is not the reality. It is the clock behavior that creates this effect. Well, this slide shows you how the combinational logic circuit work. The output at any time t, the output at any time t is completely dependent on the input at that time t. And this signal diagram also describes this. For example, for the time duration 1 with input A, the output is some function of A. Similarly, for this time duration 2 with input B, the output is some function of B, and this process goes on. So let me say that again, that a combinational circuit is a circuit in which the output at any time t is completely dependent on the input at that very time. Output at time t is actually a function of input at that time. Well, the sequential circuit is a bit different. The output of a sequential circuit at time t depends on the input at time t minus 1, which is normally called the state, and optionally maybe on the current input as well. Excuse me. And let me describe this using this signal diagram now. Well, at time 2, the output depends on the input at time 1. This is the input at time 1 or the state of this chip at time 1. The output at time 1 at time 2 is basically a function of the state at time 1. Similarly, at time 3, the output depends on the input at time 2. Similarly, at time 4, the output depends on the input at time 2. And this process goes on. Let me further illustrate this process for a very clear concept. Uh, Suppose there are discrete time signals 1, 2, 3, 4, 5, and so on. And suppose that at time signal 1, the state of the system is known to us, and that is A. So the state at time 2 will be a function of the state at time 1. Similarly, the state at time 3 will be a function of the state at time 2, and the state at time 4 will be a function of the state at time 3, and this process goes on. Now the question is, how can we move some information from time t minus 1 to time t? How can we move this state A at time 1 over here at time 2, and how can we move the state at time 2 to this function at time 3, and so on. Well, this is the block diagram of a sequential circuit. Observe this red dotted line, and we have a set of inputs coming in and set of outputs going out. Inside this block, we have two further blocks, this block of combinational circuit and a block showing flip-flops. Well, this combinational circuit output goes to another block over here, and this is again a circuit which depends on the current input as well as the previously stored output in the flip-flop. So if I say overall this circuit is a sequential circuit whose output at any time t depends on the input at that time as well as the stored state at time t minus 1. Let me repeat this line again. This is a block diagram of a sequential circuit whose output at any time t depends on the input at that time as well as the previously stored state at time t minus 1. Well, dear students, you have studied the flip-flops in the course of digital logic design, and let me quickly brush up the concepts. So to design sequential circuits, we need a chip that can remember the state of the circuit. That is, remember one bit of information from time t minus 1 so that it can be used at time t. The circuitry that we have used so far, moving some information from time t minus 1 to time t is still missing. And this bit of information can either be 0 or 1. So the state that we want to store is either a 0 or a 1, a single bit. The gate or chip that can flip between two stable states, that is, remembering a 0 or remembering a 1, is called a latch. And it can, of course, be designed using two cross-coupled NAND gate. And you must have studied the limitation of latches and how uh, we can construct flip-flops by uh, combining these latches in a master-slave configuration. Well, this slide shows a summary of the four different flip-flops that you have studied with their graphic symbols: the RS flip-flop, the D flip-flop, the JK flip-flop, and the T flip-flop. RS flip-flop has two inputs, R and S, and this is the clock, and this is the output of this flip-flop. Similarly, D flip-flop has only single input, JK flip-flop has two inputs, and the T flip-flop has a single input. Uh, these are the behaviors. The behavior of RS flip-flop is if R and S both are 0, then the new state is equal to the old state. And if S and R both are 1, then its behavior is undetermined. And otherwise, the new state is whatever is there on S. The D flip-flop is very simple. Whatever is there on D is the next state. In case of JK flip-flop, if J and K both are 0, then the next state is equal to old state. If they both are 1, then the new state is the complement of the old state. And otherwise, whatever is there on J goes inside the flip-flop. In case of T flip-flop, if T is equal to 0, then new state is the old state, and otherwise the new state is the complement of the old state. Dear students, these are the characteristic tables of all these four flip-flops. And a characteristic table, as you all know, defines the next state of each flip-flop, the next state of each flip-flop as a function of its input and the previous state. And the same is also shown over here in the characteristic equations of these four flip-flops. There is another table that I have shown only for the D flip-flop. This is called the excitation table, that is useful during the design of sequential circuits. Dear students, during the design process, we usually know the transition from the present state to the next state, and we want to find out the flip-flop input that will cause this required transition. So if we know that the present state is 1 and the next state is 0, so what should be placed on this input D that has caused this transition? So this transition table describes this. Uh, since in this course we will be designing all the sequential circuits of hack computer using the T flip-flop. So in the upcoming slides, I will be talking more about D flip-flops. So if you don't know much about the RS, JK, and T flip-flop, you need not to worry as far as this course is concerned. Well, we can of course design a D flip-flop using the built-in NAND gate available in our hardware simulator. You create a unclocked latch and then use a master-slave configuration to create a flip-flop. And this is the configuration for a negative edge triggered flip-flop. Well, dear students, uh, you can always try to create a latch inside your hardware simulator, but the hardware simulator we are using right now does not permit combinational loops. So we cannot build this DFF chip using the HDL. Fortunately, the way we have a built-in NAND gate, similarly we have a built-in D flip-flop gate or chip that is available as a built-in chip in the hardware simulator. So we will be designing and building all the sequential chips of our hack computer by using these built-in DFF chips, D flip-flop chips. Well, dear students, the way we have designed all the combinational circuits using the built-in NAND gate, as I've already said, or the helper chips that we ourselves have designed using that NAND gate, in the same fashion, we will design all the sequential circuits using the built-in DFF gate. And this is the HDL for the built-in DFF gate. From the chip interface over here, you can see the name of the chip is DFF, and it has a single bit input called in and a single bit output named out. And the implementation part shows that it is a built-in clocked chip implemented as a Java class inside the hardware simulator. Okay, so let's try to understand the behavior of D flip-flop using this timing diagram. The D flip-flop is the simplest state-keeping gate. The gate outputs its previous input, that is, out at any time t will be equal to the in at time t minus 1. So due to this behavior, it is also called a data flip-flop. Well, dear students, suppose this is the time unit 1, and at time unit 1, the in is, of course, 1. The output will be the in at time t minus 1, which is not known to us, so I have kept it blank. At time unit 2, the in is, of course, 0, and the out will be whatever the state of the D flip-flop is. That is, whatever was there at time t minus 1 at in. So the time t minus 1 at in we have 1, so the out will be 1 over here. Similarly, at time 3, uh, the out will be whatever is in at time 2, and at time 2 we have a 0 at in, so we have a 0 at out at 3. Similarly, at time 4, the out at time 4 will be the in at time 3, which is 0. So we have 0 over here. Similarly, at time 5, the out at time 5 will be the in at time 4. So you can observe we have a 1 over here because we have a 1 at time 4 at input. So once again, we need to move one bit of information from time t minus 1 to time t, and we are quite much successful in it using the D flip-flop. Well, this slide once again shows the comparison between the combinational and the sequential circuits. The output of combinational circuit is a function of its input, while the sequential chips always consist of a layer of flip-flops. We will be using D flip-flops. They may be sandwiched between optional combinational logic layers, and the output of sequential circuit is a function of its input as well as its previously stored state. And this slide summarizes the concept of sequential chips. The output or the state of the sequential circuit at time t depends on the current input as and the stored state, which is of course depends on the input at time t minus 1, as we have seen on the previous slides. Every sequential chip that we will design in our upcoming session will contain at least one D flip-flop and may also contain some other elementary logic gates. The way we have designed all our combinational circuits so far, from the built-in NAND gate provided by the hardware simulator and implemented as a Java class. Similarly, we will be designing all our sequential circuits in the upcoming part of this course using the built-in D flip-flop gate provided by the hardware simulator, also implemented as a Java class. Okay, dear students, that is all the theory and concept about the sequential circuits. And these are the tasks you need to do. First of all, I would like you to grasp the concept of all flip-flops, their graphic symbols, their behavior, using the respective characteristic tables, characteristic equations, and excitation tables. Well, you should also know as to how to perform analysis of sequential circuit as well as how to design a sequential circuit. And I think this part has been done in your digital logic design course as well. Well, you may also try to run the built-in DFF chip in the hardware simulator to fully understand its behavior. Well, I hope today's session was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. I wish you all the best, happy learning, and Allah Hafiz.